Hi, my name is Anika Valerio, and this is my lab report for Lab 2 in Physics 2211. The purpose of this lab is to observe the trajectory of an object moving in 2D motion with and without drag, using both a real-time video and prediction models. The models and principles involved include Newton's second law, which is force equals mass times acceleration, or force equals change in momentum over change in time, the velocity update formula, the position update formula, the drag force formula, and the force due to gravity. Assumptions and initial conditions include no movement in the z direction, constant acceleration due to gravity of 9.8 meters per second squared, and the origin will be at the point from which the object was thrown. So here's a preview of the data. This is the graph, and you can see the trajectory of the model with no drag is much larger than the trajectory of the model with drag and the trajectory of the experimental data. So the main ideas involve movement and projectile motion with and without drag. So we're trying to see the effect of drag on the motion of an object. So the system is the thrown object, which in this case will be a paper ball, and the surroundings include the earth and the person throwing the object. So for the video setup, there's a meter stick used as a basis in the tracker, a paper ball, which is the object thrown, a camera recording the video, and the person throwing the ball. For the recording, the point from which the object was thrown was slightly above the table in the video. So this is what the video looks like. And so for the tracker process, the origin was at the point from which the object was thrown. The axes are normal, so positive x to the right and positive y going up, even though the object was moving in the negative x direction, and the basis was based off of the meter stick in the video. The time interval was 1/30th of a second, and the point that was tracked was the center of the ball. So this is the video used in the tracker, and you can see here's a still video of what happened. The purple lines are the axes, the blue line is the basis based off the meter stick, and the red diamonds are the points that were tracked. You can also see x position versus time, y position versus time, and all the data points in the table on the right. So for the coding process, I used the starter code, and I changed the mass, the initial position, initial velocity, the time interval, the end time, the force equation, which was changed to net force equals force due to gravity plus force due to drag, and the b value was changed for the with drag model. The initial velocities were taken from the average velocity of the first 2 points from the tracker data. So here are the parts of the code. You can see the mass of the ball was 0.0035 kilograms, initial position, initial velocity, which was multiplied by 2 because there was an issue with frame rates. Initial time, delta t, gravity, final time was 0.54 seconds. The force equation, the velocity equation, the position equation, and here you can see the no drag b value is 0 and the with drag b value is 0.0045. So here's what the code outputted in terms of trajectory. So the left image is the trajectory without drag and the right image is the trajectory with drag. And then the data was put into Excel. There were 3 data sets, and I graphed all 3 data sets on the same graph. So here are the 3 data sets, and here's the graph that you saw earlier. So for similarities, all 3 models had the same starting point and the same general direction of motion, but the trajectory was very different. The no drag model's trajectory was much larger than the model with drag and the observational data. The observational data and the with drag model were similar but not exactly the same. The possible sources of error include a difference in frame rate, movement in the z-axis, camera warps, and a not completely accurate b value. So if the object was thrown straight up with the same initial speed, it would take the same amount of time for the object to reach the ground. In both the original scenario and this new scenario, the only forces affecting how long it takes for the object to reach the ground are the forces in the y direction, which are the gravitational force and drag. The gravitational force is always constant. The drag force is not constant, but it will be the same at any given time in both scenarios because the y velocities are the same at any given time in both scenarios. So this makes the y position the same in both scenarios at any given time, so they will hit the ground at the same time in both scenarios. For terminal velocity, my models do not predict a terminal velocity. In order to find the terminal velocity, the ball would have to be dropped from a much higher height so that it has enough space and enough time to reach its terminal velocity. At that point, the force due to gravity and the force due to drag should cancel out, making the object's velocity constant. So in conclusion, for a paper ball, drag makes a significant change in its trajectory.